Today's topic is numerics. Like basically we are gonna see some topics that are relevant to math, which can be very handy when it comes to solving competitive programming questions, as well as dealing with the problems in the interviews. And the first thing that we are gonna look at is prime numbers. I think everybody is familiar with the definition of a prime number, right? If a number cannot be divided evenly by itself anything except itself and 1, then we say this number is prime. And the only exception is 2, because for 2 that is the case. But since there is no other number, still we say it's prime. So to find the prime, to figure out whether a given number is prime or not, we can actually apply a very simple algorithm, right? Can somebody tell me which algorithm is it? How can we check whether a given number is prime or not?
We iterate to every number from 1 to up to itself, and if it's divisible by more than 2 of them, by any other number. So
yes. So basically what we can do is, oops. Like we can have one for loop. Let's say our function is Boolean is prime. Let's say it's prime naive. And obviously we are getting an integer as a parameter. Let's say it is n. And in the end we want to decide whether this number is prime or not. And what we are going to do is Caleb suggested, like we can basically start from 2. And we can go up to n and say if n mod I is equal to 0, then return true. Otherwise, return false. So, this algorithm would work, right? Okay. Is there anything that looks a little bit inefficient here? Like, is there something that we can do a little faster? Yes.
We can go until n over 2, so we can eliminate half of the numbers.
That's a good one. Asymptotically speaking, it's not going to make any difference, but in practice, it's going to make a difference, right? And in some of the interviews, they might actually care about the practical differences. Like it's just like you should basically know what's happening, right? You should know that it doesn't make any asymptotic difference, but it makes difference in practice. Okay, so now we have a little bit of faster algorithm. Can we do any better?
We can do 2 square root of n.
We can?
2 square root of n.
So instead of going to n over 2, we can actually go up to square root of n. Why?
The other half is the multiple of the first up to the square root of n.
Yes, so basically I think what you're trying to say is, let's say, if our number is divisible by a, it means the number can be represented by a times b, right? And this a and b, let's think like in what circumstances the minimum of a and b is going to be the maximum. Like once they are closer to each other, the minimum is going to go up, right? Like let's say for example n is 100. And if our multipliers are 2 and 50, the minimum is 2. But if our multipliers are 10 and 10, the minimum is 10. So if we are looking for the maximum minimum, then we actually try to make them as even as possible. And actually that case only happens once we get the square root, right? So now let's think about our sign. Should it be less than or less than equal to? Less than equal to, right? Because otherwise we would miss I mean, it would be caught by other multipliers in this case, but like for example, we could have missed it for 9 if we didn't have the equality sign, right? So, any questions up to this point so far? And I think still, we are focusing on our first problem, right? Checking if a number is prime or not. So, any questions up to this point so far? Like, right now our time complexity is down to square root of n, right? Imagine that we can do some pre-computation. With some pre-computation, can we actually get better than this?
You could perhaps keep track of prime numbers and then only use them.
Right? Because is there a point checking the numbers that are not prime? Because they are divisible by the previous prime numbers, right? So if we have a chance, let's say we can get primes as parameter here. What we can do is, instead of iterating up to square root of n, we can basically iterate on this primes array until we get to an element that is greater than square root of n, right? So let's do that modification. Assuming all the primes are listed in a sorted order in the primes array, we can start from 0, and as long as primes I is less than or equal to square root of n, we can keep going. And this time we are not going to check the modulo against I, we are going to check it against primes I. All right, so now we actually have even faster algorithm, right? We don't go over all the numbers up to square root of n. We are only checking the prime ones because the ones that are not prime are divisible by the smaller primes already. So there is no point checking them again and again. If the prime number that was dividing that number is not dividing this number evenly, then there is no way that number can, or all the primes are not dividing it evenly, then that number is not going to divide it evenly either. Cool. So I think we get to a very optimal algorithm at this point. But now we have a new task. We added a new parameter here, right? So we have to fill this up. How are we going to calculate these primes? Now that we have this function, but we cannot use this function anymore, right? And it's not naive anymore, so let's also delete this part. But like one thing that we can do, like imagine we didn't add the prime parameter yet. Primes parameter yet. Let's go back to the previous implementation of his prime. Can we populate this array with the help of that function? How can we do that?
Using the we can check if the number is prime and then add it.
Yes, right? So let's say if our function is gonna support things up to 1 million, we can basically have a loop from 1 to 1 million and then check if the number is prime or not. And if it is prime, we can add it to our array. So that's one way of doing it. But actually, there is a faster way of constructing this primes array as well. And did anyone ever hear about the SIEVE of Aristotle? Or maybe I'm not pronouncing his name correctly. ERATOSTHENES or something like that. I'm not a native speaker either. So, basically the idea is that, like instead of trying to check all the elements one by one, what we can do is, we can basically mark the numbers that are the multiplication of the smaller numbers. Let's say we know that 2 is prime. Any number that can be reached by multiplying 2 with a natural number, is it possible that that number is going to be prime? No way, right? So the algorithm is actually making use of that. So now let's take a look at the code. So at the beginning, all the numbers are prime for us. Because this time, instead of trying to find the prime numbers one by one, we are eliminating the numbers that are not prime. So everything starts by default as true. And at the beginning, obviously, we know that 0 and 1, they are not primes, right? So this is kind of our base case. And then we say these numbers, we mark them as not prime. And after that, we get the square root of the number that we want to fill our prime array up to. So n here does not represent number of primes, but the maximum prime that you want to basically populate all the primes up to n. And in order to do that, actually looking for all the numbers that are less than or equal to the square root of m is enough. And now let's look at the algorithm, how it works. So we start from 2. And then we check if this number is prime or not. Like the reason we do this check is actually to make things faster. If a number is not prime, it means it is already marked by a smaller prime before, right? So that's why, is there a point in checking its multiples and marking them as not prime? No, like you can think of this as after marking multiples of 2, do we have to mark multiples of 4? No, they are already marked by 2. So that's why we have this check over here, to make things a little bit faster, basically. And inside, what we are doing is, so we start from the square of this number, here as you see. K is equals to I times I. And then we continue until our limit, and then we keep increasing it by I. So can someone tell me why we are starting from I times I, but not I?
Because we don't want to remove I.
What's that?
Because we don't want to remove I, and then we just want to remove its multiples.
Yes, but we also don't start I times 2. It starts from I square. Yes?
So we avoid the stuff we already marked before. For example, 4 times 2 has already been marked by 2 times 4. So we don't want to go back there.
Yes. Like basically we are making use of the first elimination that we have seen. So if n is not a prime, it means it is a times, it can be represented as a times b, right? And for the numbers that are smaller than the square of a, if n is multiple of those, like one of the multiples is going to be greater than the square root, but the other multiple is going to be smaller than the square root. So that's why, with the help of that smaller than the square root multiplier, we would have marked this number. So that's why we don't have to start from I times 2. It's okay to start from I square. Because all the smaller non-primes are marked with the help of the smaller multiplier. Is this clear? Like even in such a short amount of code, like there are some prunings and improvements that we can apply, right? I mean here, obviously not applying this if condition and starting from 2 is going to make our algorithm slower. And I want you to test this, like actually see how much of an improvement we get by such kind of prunings, okay? Because the reason I want you to see is that such kind of things can actually matter a lot in practice. Like asymptotically speaking, maybe it's not going to make any difference. But in practice, such kind of prunings can actually make things way faster. So, any questions up to this point so far? Yes?
So, I really didn't get the point why we use square root principle. I didn't get the reason behind why we are doing the square root, x is less than square root of.
Why are we going up to square root but not more than that?
Yeah.
Okay, so it's actually coming from here. Like if number n is not prime, then it means we can represent it in a way that a times b with the natural numbers where a and b are not equal to n or 1. Right? So let's consider the case like, let's consider different cases. So in order to maximize the minimum of a and b, because like if we just check the minimum one, that would be okay, right? Like our example was 100. like we can write 100 as 2 times 50. At the same time, we can write 100 as 10 times 10, right? So in the case of 2 times 50, if I check by 2, then I will be able to tell that 100 is not prime, right? So basically what I really care is the smaller multiplier. Because there is no point going up to the larger multiplier. Because with the help of the smaller multiplier, I would be able to mark that number as not prime anyways. Okay? So, now that we know that our focus is the smaller multiplier, let's see what is the maximum value of the smaller multiplier. So, the maximum value we can get is, for the smaller one, is when these two numbers are equal, right? So in the case of 100, when we are testing 10, we get the smaller number maximum, okay? So, and this is happening when they are equal to each other, and when they are equal to each other, this number is actually the square root of n, okay? So that's why, if we go up to 10, we can actually guarantee that we checked all the possible small divisors. Okay? Any other questions? Cool. Then let's continue with the next topic. So, are you guys familiar with the term greatest common divisor? It's actually very self-explanatory, right? So we are given two numbers, and we are trying to find a number that divides them evenly, like which number is the greatest that divides them evenly. So, let's continue with an example. Let's say we have 130. So for this example, I think they are both divisible by 10, right? And is there anything that is higher? This is not divisible by 15. This is not divisible by 20. I think 10 is the answer for these two numbers. So, again, as in the case of the prime number check, can you come up with a simple, naive algorithm? Like, how can we find the greatest common divisor? Anybody? Is it that hard, or you just don't want? Any hands? Come on, Yamachu.
So we are trying to sort the two numbers, and then after we get which divide them both equally. After that, we will sort it arithmetically. After that, if you get the highest number, we return it as the after reaching the smallest number, and we iterate through the numbers. So when we get
That divides them both?
we will return.
We return that. But which way do we start? Do we start from one and go up to the smaller one, or do we start from the smaller one and then come down?
Okay, I think from the smaller one down to return.
We're gonna come down, right? Because that way, like, we can basically tell that the first number that we find is gonna be the answer,
Yeah.
right? Okay. So did everyone get the algorithm? Like, just for the sake of completeness, let me write it. We have A and B. And then we start from the smaller one. Candidate is equal to, well, let's say, C is equal to minimum of A and B. C is, so in the worst case, what's the minimum value of the greatest common divisor? Right? C is greater than 0, C minus minus. If A mod C is equal to 0 and B mod C is equal to 0, then return C. Actually, we don't have to add a return statement here, but probably the language is going to complain, like the compiler is going to complain, so here we can add this return -1 to confuse people. So, I guess the naive algorithm is clear to everybody, right? Okay, now let's think about how we can make this faster. Like, let's take a look at here. We actually have a hint here. Like, can we say that for any kind of A and B pairs, we can have an equation like A is equal to B times, is it X? Yes. X times B plus C.
Yes.
Right? So, the second question is, like basically here what we are doing is we basically divide A by B, and then X is our divisor, and then we have here C. I guess like you guys are representing division in a different way, right? But is it okay? I think you are able to follow, right? Okay. So I forgot your representation, but this is how we do it, so. Okay, so now let's think about this. So this basically means that the remainder of this division is C, right? And A is equal to X times B. So now let's focus on these numbers. If we are talking about the greatest common divisor, would that greatest common divisor divide X times B evenly? Right? Because I mean it has to divide B, otherwise it cannot be greatest common divisor. So if this part is evenly divided, then we know that the mod, let's say our, now I use C here, let's say the result is greatest common divisor is GCD. We know that X times B mod GCD is equal to 0, right? So now let's think about the summation here. The summation is A. And since we know that greatest common divisor also divides A evenly, what can I say about the mod of greatest common divisor for this term here? This is also equal to 0, right? So if this is equal to 0, this is equal to 0, what is the mod of C with greatest common divisor? It is also 0, right? So, what did we discover now?
Greatest common divisor of C and B.
Greatest common divisor of A and B is equal to what? Greatest common divisor of B and C. Yes. So, how can we make use of this information to make this algorithm faster?
Finding the reminders and then finding the GCD of the reminder and then.
Right? So basically, oh, this was GCD naive. And now I'm going to delete this. And here basically we are going to say, so what's going to be our base case? When are we going to stop? If A mod B is equal to 0, then what can I say? What's that?
Just return.
Just return which one?
Yeah. Just B, the smallest.
What's that?
B, the smallest one.
Yeah, let's say where B is the smaller one. I mean, if B is the greater one, there is no way it's going to be 0, right? So I think this check is safe in both cases. And if that is not the case, then what we are going to return? Like basically, we are going to get the remainder, and we can get the remainder with the mod operation, right? Would this work? Obviously not. I need a function name.
Also, wouldn't you want the bigger one on the left side?
Yeah.
Would it make a difference?
Since we're checking the A multiple B.
Like, let's say if A is bigger, then this is gonna work as we expected, right? What if A is smaller?
0.
If A is smaller,
No, we return
We reverse.
the one we returned though. We're returning B not
what's that?
the one we're returning. No, and the base case. Would it not make a difference if A and B have shifted?
Here.
Cases? Yeah.
So that's why we actually, or alternatively, we can change the parameters here, right? We can basically say B is going to go here, and then A mod B is going to go here, right? Okay. So any questions about this one? All right. So now we also have a working greatest common divisor code as well. And here actually in this code, it used another AND condition. Once B is equal to 0, return A. But once B is equal to 0, then A mod B is also gonna be 0. So that's why I think that should work. And if A mod B is 0 at that point, I don't think there is any risk on returning B, because in the next step it's gonna go down to 0. So I think both conditions are equivalent. But maybe mod operation might be a little, we are actually getting the mod anyway, so we can do it. We can basically apply the mod operation here and say mod is equal to A mod B, and then just use mod here, just to avoid calculating the same thing 2 times. Okay? So depending on how many times we are going to call this function, even such kind of an improvement can make a difference. But for that, like, you have to call this maybe billions of times. So, okay. So after greatest common divisor, now we get to the lowest common multiple. I guess you guys are also familiar with the definition of lowest common multiple as well, right? So basically, this time we are given 2 numbers A and B, and we are looking for the smallest number which can be evenly divided by both A and B. And for this one, actually, since we have the greatest common divisor anyways, there is one nice property. Like, basically the multiplication of these 2 numbers is equal to multiplication of greatest common divisor and lowest common multiplier, or lowest common multiple. Why is that? Why is there such magic? Okay, now you have a homework for the vacation. I mean, it's not that complicated, but it would be nice to know that, right? All right. But like, since we know that this is the case, and we are going to figure out after the homework why this is the case, we can actually make use of this information. And obviously, just multiplying these 2 numbers and dividing by the greatest common divisor is going to give us the lowest common multiple, right? But there is one thing that you should be very careful here, because we are making a big multiplication here. Like, if A and B, they are both integers, there is no guarantee that A times B is going to be integer, right? So that's what you should keep in mind. Like, I don't really like this implementation much, because it doesn't work for like a huge range of integers. Basically, it assumes that the multiplication of the 2 integers is going to fit 2 integers. So it's better to make this maybe long int. Like, even our parameters are int. Okay? Like, we should always be careful about the extreme cases. Overflow, we hate overflow. Except Stack Overflow. It's a lifesaver for software engineers. Alright. And the next topic that we are going to cover is bases. So, like, basically for some questions we might have to convert numbers from one format to another. And like, most common ones are converting from a given base to decimal, or from decimal to a base. But obviously, like, you can generalize this and you can convert from base I to base B, base A to base B. And now let's think about it. Have you guys ever done this number conversions before? Probably you did, right? How can we do that? Can someone just quickly summarize the first one? Any hands? We need more volunteers, guys, come on. Linda. Yes.
From B to decimal.
Yes.
So we take the number and then multiply it by the base, and then
Add that to the result and then go to the next digit. And when we are going to the next digit, we also multiply like our base indicator with the base, so that like we know that we are on the second one, and we keep going. It's very straightforward, right? And let's also talk about the second case where we convert a decimal number to B. Daniel, our son of our team.
When we have a decimal number, change it to binary, we divide it by 2, and we keep doing that and keeping the remainders, and then we reverse that order of the remainders.
Oh, you are talking about decimal to binary, right? And instead of binary, if it's just base B, then instead of 2, we are going to be dividing it with B, right? Yes. Okay. Cool. So, I mean, since everybody is familiar with this and it's not very complicated, I'm not going to go into details here. But the next topic is actually important. And you guys have already seen some problems in which you could have used this information. So, the next thing that we are going to cover is how we are going to deal with fractions. Like, first off, like the best way to represent fractions is to keep numerator and denominator separately. Like instead of keeping it as a ratio, because one ratio can be matched to multiple things. And as you know, like double precision is not perfect in our programming languages, right? So that's why it is important to represent them mostly or like almost all the time with numerator and denominator, okay? So you can use pair, you can use an array of 2, like any way you want, you feel comfortable with. But the point is to keep numerator and denominator separately. So now let's take a look at some operations. The first operation we are going to cover is multiplication. Actually, multiplication is very simple, right? If we are given like A and B, A over B and C over D, the multiplication is A times C over B times D, right? This is very simple. But there is one thing that we should be careful with, which is we are doing multiplication again here, right? If everything is integer, there is no guarantee that the multiplication is going to fit to integer. So you should be aware of the risk of overflow, okay? But rather than that, there is nothing to worry about. So the second operation is a little bit trickier. When we want to do summation, we can actually make use of the previous functions that we defined, right? So in order to be able to sum the numerators, we need to have the same denominator, right? And with the help of lowest common multiple function, we can basically find the lowest possible denominator that both fractions can be converted into. And with the help of that, we just do basic summation operation. So let's take a look here. Like first we get the lowest common multiple of A1 and B1. A1 and B1 are the denominators. And after that, we say the new fraction that we want is denominator over A1 times A0 plus denominator over B1 times B0. Like there is basically a little bit of basic algebra here to get these formulas. You don't have to get the formulas. Once you get the lowest common multiple, like the idea is very simple, right? So if it was AB over CD, like how would we do it in a naive way? We would do it like B times A plus C times B over BD, right? But the thing is, in this way, this is not going to be in the form of the most reduced form, right? So, another thing that we should be careful with when it comes to fractions is that most of the time, almost all the time, there is no point in not keeping them in the most reduced form. Meaning, like if there is a common divisor between the numerator and denominator, then we want to basically divide them and keep it in the simplest form. For example, if we are dealing with 5 over 10, instead of representing it as 5 over 10, it's better to keep it as 1 over 2. Like there is also another value here. When we apply such operations, we have the risk of overflow, right? And if we keep everything in the simplest form, then things are going to be easier. And the second point is, in competitive programming problems, most of the time we want to have a unique result, because then it's easier to check. Like if you don't have a unique result, you have to write a program to control whether the given numbers are correct or not. But if you have a unique result, you can just say diff, right? It's going to be easier to check. So that's why in many of the competitive programming problems, you are going to have a unique result. And when it comes to fraction problems, in order to get the unique result, everything has to be represented in the simplest form. Okay? So the next operation we are going to take a look at is reduction. So, and for reduction, again, it's a very simple operation with the help of the functions that we defined before, right? So what we are saying is basically, if there is a common divisor between numerator and denominator, I want to divide them both with that number. Actually, the greatest common divisor, so that it's going to be turned into the simplest form. So, any questions up to this point so far? Like, as you see, approaching things constructively actually makes our job way easier. Like, if we didn't have our lowest common multiple and greatest common divisor functions, then when it comes to implementing these reduction and summation, we were going to do it again and again, right? And right now, with this abstraction, we don't really have to learn the same thing in different places with the same complexity. We can learn it once. Now that you know how GCD works, right? With the help of mode operation, we have a very efficient and very simple greatest common division finder. And to get the lowest common multiple, we are getting the multiplication and divided by the greatest common divisor. So they are both very simple. And in the end, with the help of these functions, we can also get very efficient and simple fraction operations. So any questions up to this point so far? No questions? All right, so this was the last topic. And as always, we have the quote of the day. But this time, the quote comes from a Turkish leader, Mustafa Kemal Atatürk. So he is the founder of modern Turkish Republic. And this saying of him, it's actually very famous. If one day my words are against science, choose science. So he wasn't in love with his thoughts. Like he actually accepted to give up on them. Actually suggested us to give up on them in case they contradict with science. And I think that's a very good point. Thank you very much.